The universe is full of mysteries, but few are as captivating and terrifying as black holes. Imagine a cosmic entity with a gravitational pull so intense that not even light can escape its grasp. For a long time, these enigmatic objects were thought to be invisible, silent vacuum cleaners, lurking in the dark and waiting to consume anything that wandered too close. However, the reality of how black holes interact with their surroundings, particularly when they encounter a star, is far more violent and spectacular than simple cosmic vacuuming. The process by which a black hole devours a star is a brilliant, destructive dance known as a tidal disruption event, and it reveals some of the most extreme physics in the entire universe. To understand how a black hole eats a star, we first have to understand the nature of gravity near these cosmic behemoths and the types of black holes that exist. While stellar mass black holes, born from the collapse of massive stars, roam our galaxy, it is the supermassive black holes that are the true gluttons of the cosmos. Residing at the centers of almost all large galaxies, including our own Milky Way, these giants can have masses ranging from millions to tens of billions of times that of our Sun. At the heart of any black hole lies the singularity, a point of infinite density. Surrounding this is the event horizon, the invisible boundary of no return. But a supermassive black hole's gravitational influence extends far beyond its event horizon, dictating the orbits of millions of stars in the dense, crowded environment of the galactic center. Most of these stars orbit peacefully, kept safe by their velocity and their distance from the abyss. But the galactic core is a chaotic, bustling metropolis. Gravitational interactions between stars are common. Sometimes a close encounter with another star or a dense cluster of matter can act like a gravitational slingshot. This can alter a star's trajectory, robbing it of its stable orbit and sending it on a plunging, fatal course toward the central supermassive black hole. The doomed star might take thousands of years to complete this inward journey, oblivious to the terrifying fate awaiting it at the center of the galaxy. As the star begins its final approach, it doesn't just fall straight into the event horizon and disappear like a rock dropped into a pond. The distance from the black hole is the critical factor. As the star gets closer, it begins to experience extreme tidal forces. Tidal forces are the same gravitational phenomenon that causes the oceans on Earth to rise and fall in response to the Moon's gravity. The Moon pulls slightly harder on the side of the Earth facing it than on the side facing away. On Earth, this difference is relatively small, just enough to move water. But as a star approaches a supermassive black hole, this difference in gravitational pull across the volume of the star becomes monstrously powerful. When the star reaches a critical distance known as the Tidal Disruption Radius, the gravity pulling on the side of the star facing the black hole becomes overwhelmingly stronger than the gravity pulling on the star's far side. At the same time, the star is still desperately trying to hold itself together by its own self-gravity. A cosmic tug-of-war begins between the black hole's tidal forces and the star's internal binding energy. Eventually, and inevitably, the black hole wins. The difference in gravitational pull becomes so immense that the star is literally ripped apart from the inside out. This tearing process is not a sudden, clean explosion. Instead, it is a gruesome, stretching deformation known to astrophysicists by the highly technical and strangely culinary term, spaghettification. The star is elongated along the direction of the black hole and simultaneously compressed from the sides. It transforms from a spherical ball of hot plasma into a long, thin stream of stellar debris. This stream of gas can be incredibly long, stretching across millions of miles of empty space. In a matter of hours or days, a star that had existed as a stable, burning sphere for billions of years is unraveled into a continuous, twisting ribbon of incandescent gas. It is worth noting that the size of the black hole determines whether this spectacle is visible to the outside universe. If the supermassive black hole is too massive, specifically exceeding about 100 million solar masses, its event horizon is actually larger than its tidal disruption radius. In this terrifying scenario, the star crosses the event horizon while still entirely intact, swallowed whole without a sound or a flash of light, disappearing from the observable universe before tidal forces can tear it apart. We only witness tidal disruption events when the black hole is small enough that the star is destroyed outside the event horizon, allowing the resulting light to escape into the cosmos. But even when the star is spaghettified, the black hole doesn't swallow this entire strand of stellar material at once. In fact, it doesn't consume all of the star at all. Orbital dynamics dictate a very different fate for the remnants. Approximately half of the disrupted star's material is flung outward, escaping the black hole's gravitational grip entirely. This escaping gas is ejected into the surrounding galaxy at tremendous speeds, carrying with it the heavy elements that were forged deep inside the star's nuclear core over its lifetime. The other half of the stellar debris is not so lucky. This material remains gravitationally bound to the black hole. The long stream of gas swings around the black hole in a highly elliptical orbit, looping back on itself. As the leading edge of the stream completes its orbit and collides with the trailing material still falling in, the gas crashes into itself at significant fractions of the speed of light. These extreme high-speed collisions generate immense shock waves, heating the gas to temperatures of millions of degrees. Through this violent, self-intersecting interaction, the bound stellar material loses its orbital energy and begins to settle. It forms into a flattened, swirling structure known as an accretion disk. This disk of superheated plasma orbits the black hole, spiraling inexorably inward toward the event horizon, much like water spiraling down a drain. The inner regions of the accretion disk are subjected to intense friction and powerful magnetic forces. The gas rubs against itself, generating unimaginable amounts of heat. As the temperature skyrockets, the accretion disk begins to glow furiously, radiating vast amounts of energy across the electromagnetic spectrum, particularly in the form of ultraviolet light and X-rays. This sudden, brilliant flare of light is what astronomers observe from Earth. While the black hole itself remains completely dark, the death throes of the star create a beacon that can briefly outshine all the other billions of stars in the host galaxy combined. These sudden bursts of light are the signature of a tidal disruption event. They can last for months or even years, gradually fading as the black hole slowly consumes the material in the accretion disk. For astronomers, these events are incredibly valuable because they temporarily illuminate otherwise dormant, invisible supermassive black holes, allowing scientists to study their mass, their spin, and the extreme environments immediately surrounding them. In some rare and spectacular cases, the process of eating a star produces something even more extraordinary. As the superheated gas in the accretion disk spirals toward the event horizon, complex, twisting magnetic fields can channel a fraction of the material away from the black hole and launch it outward from the north and south poles. These structures are known as relativistic jets. These twin beams of matter and energy are blasted into deep space at nearly the speed of light, piercing through the surrounding galactic environment like cosmic blowtorches. When a tidal disruption event produces jets, the light emission is altered dramatically, sometimes shifting into highly energetic gamma rays. These jetted events are among the most violent phenomena ever observed, sending shock waves through the surrounding interstellar medium. So, what happens after the meal is over? As the months and years pass, the black hole steadily drains the accretion disk. The gas spirals past the event horizon, vanishing forever from the observable universe. The brilliant flare of X-rays and ultraviolet light slowly dims, fading back into the cold darkness of space. The black hole has grown slightly, adding a fraction of the star's mass to its own unfathomable bulk. Its gravitational pull has become marginally stronger, and its event horizon has expanded by an imperceptible margin. The galaxy settles back down, returning to its quiet state. The escaping half of the star, however, continues its journey outward. It travels through the interstellar medium, enriching the galactic environment with heavy elements like carbon, oxygen, and iron. This expelled gas might eventually cool and mix with vast interstellar clouds of molecular hydrogen. Over millions of years, these clouds might collapse under their own gravity, perhaps one day contributing to the formation of a new generation of stars and planets. In a strange, poetic cosmic twist, the violent death of one star at the hands of a supermassive black hole can physically seed the ingredients for future solar systems. The iron in the blood of future life forms could theoretically trace its origins back to a stellar disruption. For the black hole, this dramatic feast is a profoundly rare occurrence. In a typical galaxy like our Milky Way, a tidal disruption event is estimated to happen only once every 10,000 to 100,000 years. For the vast majority of its existence, a supermassive black hole sits quietly in the dark, starved of fuel, acting more like a silent anchor for the galaxy than a ravenous monster. The violent destruction of a wandering star is just a brief, fiery interruption in an otherwise silent, eternal wait. As our telescopes become more powerful and our automated surveys of the night sky become more comprehensive, we are detecting these stellar executions with increasing frequency. Instruments that scan the entire sky every few nights are catching the initial, sudden flares of these events in real time. Each new observation provides another vital piece of the puzzle, helping us understand the complex mechanics of gravity, the behavior of matter under extreme relativistic conditions, and the profound, shaping influence that supermassive black holes exert on the evolution of their host galaxies. Far from being simple cosmic vacuum cleaners, black holes are dynamic, transformative engines of destruction and creation, silently shaping the architecture of the universe until a wandering star makes the fatal mistake of coming just a little too close.